Hello and welcome back. So in our previous segment, we were talking about we mentioned the amplitude, the frequency, the wavelength, and the speed of a wave. And yet another thing that a wave can have, another property of a wave, is its frequency can change depending on its motion. And so what I want you to do is I need for you to watch this video. So go to the internet and type in Doppler Effect, what does motion do to waves? Find it on YouTube. You'll know that you found the correct video if it starts off with an episode of The Big Bang with Sheldon. All right? So watch that video. Pause me. Do it. All right, so am I paused? I hope so. All right, did you watch it? Okay, so let's talk about that video, and then let's talk about Sheldon at the end of it and talk about why he was wearing that costume. Okay, so the first thing I want you to see was that if you've got a pond and then you take your finger and you poke it, it's going to make ripples that are going to do this. And I'm trying to draw it so that each one of them is equally spaced when I go around it. So what this represents is going to be a crest. A crest. And then this is going to be a crest, and then they're connected with a trough. So can you see the wave there? So therefore, the distance from this line to this line is going to be the wavelength. So he didn't mention that in the video, but the distance between the lines would be the wavelength. Now this is what would happen if the source of the waves, which in this case was my finger poking the water, was not moving. Now, on the other hand, let's pretend that this is a sound wave and it is moving, and then what you saw was that the waves would get scrunched up in the front and then they would be stretched out in the back. So something like this. So the waves are being crowded together. Now the whole thing is moving in this direction. The waves are they're closer together. So what does that tell you about the wavelength? If they're closer together, then the wavelength is going to be smaller. And then on this side over here, the wavelength is going to be larger. Now, what does that tell you about the frequency? So if the wavelength gets small, what would the frequency do in order to compensate? Well, we know that C is equal to the wavelength times the frequency. So that was our definition. The speed of a wave is its wavelength multiplied by its frequency. So let's say that the wavelength is small. Then what does the frequency do in order to compensate? Well, you know 4 is equal to 4 times 1. But it's also equal to 1 times 4. So that what happens is this number gets bigger in order to compensate. Where have we seen that before? Up here. So a large wavelength, a small frequency. Over here, it's a small wavelength, a large frequency. So light does this. If you decrease the wavelength, then the frequency will increase in order to compensate. So that's the reason why if something is coming towards you, the frequency is going to go up. If something is moving away from you, then the frequency is going to go down. So that's called the Doppler effect. And it works for sound. So you can do it with the sound of an ambulance or a car honking its horn as it comes towards you and then away from you. But it also happens with light. So if light is moving towards you, the source of the light waves, like a star, if that star is moving towards you, then that frequency is going to go up. Okay, now what does that mean? If the frequency goes up, that means we're going in that direction, right? Okay, frequency is going up. Now, what are the colors of light? Okay, you have to remember from elementary school, Roy G. Biv. So let me write it up here. R-O-Y G-B-I-V. Now, the way that you can keep this straight in your head is notice that red is next to infrared and violet is next to ultraviolet. But look at what's happening is if the frequency is going up, do you see that that's in the blue part over here? So blue is closer to the large frequencies than what red is. So we say that if the source of the light is moving towards us, we say that the light is blue shifted. It doesn't necessarily have to be the color blue. It's just shifting in that direction towards the blue. On the other hand, if the source of the light is moving away from us, then we say it's red shifted, and see, red is closer to the shorter frequencies. So that's the difference between a red shift and a blue shift. Now getting back to Sheldon. All right, so Sheldon was wearing a particular costume. This was the Halloween episode of The Big Bang Theory. And you notice he had stripes on his shirt. Did you notice what the stripes were doing? Did you see that the stripes were getting further apart the closer it got to over here and then to over here? And it didn't show the back of his shirt, but if he had turned it around, you would have noticed that the stripes would have gotten very far apart in the back. He was dressed as the Doppler Effect. So that was his costume for Halloween. So if he was walking towards you, the lines were close together, and then that was representing a short wavelength or the higher frequency. And then as he walks away from you, then the lines are getting further apart. You're not even interested in that. I thought it was very funny. Of course, then again, I'm a scientist. I find that kind of stuff very funny. Okay, let's take a break. And when we come back, we're going to talk about what happens when light encounters matter. See you then.